It begins with a single question, whispered not in a lab, but in the silence between stars. Why doesn't the universe fly apart? Look up on a clear night. The Milky Way stretches across the sky like a river of ancient light. Billions of suns swirling in a grand, slow dance. But something is wrong with that dance. If you watch how the stars move, especially those far from the galactic center, they're spinning far too fast. So fast, in fact, that the visible mass of the galaxy, the stars, the gas, the dust, shouldn't be able to hold them. Gravity, as we understand it from Newton and Einstein, says those outer stars should have flung themselves into the void long ago. Yet they remain, bound, orbiting, as if held by an invisible hand. This isn't just true for our galaxy, it's true for nearly every spiral galaxy we've ever observed. And it's not just galaxies. Look at clusters, great cities of galaxies bound together by gravity. In the 1930s, a Swiss astronomer named Fritz Zwicky pointed his telescope at the Coma cluster, a swarm of 1,000 galaxies drifting through space. He measured how fast those galaxies were moving relative to one another, and what he found defied belief. The galaxies were zipping around so quickly that the cluster should have torn itself apart in a cosmic instant. There simply wasn't enough visible matter, no matter how you added up the stars and gas, to create the gravity needed to keep it all together. Zwicky called the missing ingredient dunkle materie, dark matter. Few listened. His idea seemed too strange, too convenient. A ghost invoked to save a theory. For decades, dark matter remained a footnote, a curiosity dismissed as a miscalculation or an overinterpretation. Then, in the 1970s, another astronomer, Vera Rubin, began meticulously tracking the rotation of stars in Andromeda and other nearby spirals. Night after night, she and her colleague Kent Ford recorded the faint light of stars at the very edges of galaxies. And again, the data told the same impossible story. Stars far from the center were orbiting just as fast as those near the core. In a normal system, like our solar system, the farther you are from the center, the slower you move. Mercury races around the sun, Neptune crawls. But galaxies don't behave that way. Their rotation curves, graphs of speed versus distance, should slope downward. Instead, they stay flat, like a plateau stretching into the dark. That flat line is the fingerprint of something unseen, something massive, something that doesn't shine, doesn't absorb light, doesn't interact with the electromagnetic force at all. It only reveals itself through gravity, the most ancient and universal of forces. Rubin's work was painstaking, precise, and impossible to ignore. She didn't shout her conclusions, she let the stars speak. And what they said changed everything. The universe, it turned out, is not what it seems. The stars we see, the brilliant beacons that have guided sailors and poets for millennia, are just the tip of a vast hidden iceberg. For every gram of ordinary matter, the atoms that make up planets, people, and pulsars, there is roughly 5 times more of this dark, invisible substance. It forms a great cosmic scaffolding, a web of unseen mass upon which galaxies are built. Without it, the universe would be a scattered, formless fog. No galaxies, no stars, no us. But how do we know it's really there, and not just a flaw in our understanding of gravity? The most stunning proof came not from motion, but from light itself. Einstein taught us that mass bends space-time, and light follows that curve. So when light from distant galaxies passes through a massive foreground object, like a galaxy cluster, it gets distorted, stretched, magnified. This is gravitational lensing. And when astronomers map the lensing around clusters like the Bullet cluster, a violent collision of two galaxy clusters, they see something extraordinary. The visible matter-hot gas, glowing in X-rays, slams together and slows down, stuck in the middle like wreckage after a crash. But the mass, the thing causing the lensing, keeps moving ahead, separated from the visible stuff. It's as if two clouds of smoke collided, but the wind that carried them kept blowing. The mass is where the galaxies are, not where the gas is. And that mass is dark. It doesn't collide. It doesn't emit. It just flows through itself and everything else, ghost-like, shaping the path of light across billions of light years. This is not speculation. This is observation, repeated, verified, confirmed by satellites like Flung, which mapped the faint afterglow of the Big Bang, the cosmic microwave background, and found patterns that only make sense if dark matter makes up about 27% of the universe's total energy content. Ordinary matter, just 5%. The rest is something even more mysterious, dark energy. But that's another story. So we stand at a threshold. We've mapped the shadows cast by dark matter across the entire observable universe. We've seen its hand in the birth of galaxies, in the bending of light, in the very structure of the cosmos. We know it's there. We know how much there is. We know how it clumps, how it flows, how it shaped the universe from its fiery infancy to the present day. But we still don't know what it is. Not truly. Not in our bones. Not in our detectors. And that's where the real mystery begins. Because the simplest answer, that dark matter is made of one kind of heavy, slow-moving particle that barely interacts with anything, might be wrong, or incomplete, or just the first chapter in a much stranger tale. What if dark matter isn't a single silent ghost, but a whole hidden world? What if it has its own rules, its own complexity, its own secrets waiting in the dark? The universe has already shown us that reality is far stranger than we imagined. It gave us black holes, quantum entanglement, expanding space. So why should dark matter be simple? Why should it play by the rules we've written for the world we can see? The evidence is clear. Something invisible holds the cosmos together. But the nature of that something, its true identity, its hidden depths, remains one of the greatest unsolved puzzles in all of science. And the answer, when it comes, might not just explain the missing mass. It might rewrite the laws of physics. It might reveal a universe far richer, far weirder, and far more wondrous than we ever dared to dream. The hunt is on, not for something that might exist, but for something that must exist. And the first step isn't in a lab or a telescope. It's in our willingness to imagine that the darkness might be stranger than we ever thought possible. For decades after Vera Rubin's Quiet Revolution, the scientific world settled into a kind of hopeful certainty. Dark matter existed. That was no longer in doubt. The question now was not if, but what. And the answer, many believed, was already written in the elegant mathematics of particle physics. It wasn't just a placeholder for ignorance, it was a prediction waiting to be confirmed. The leading candidate emerged not from astronomy, but from the deepest theories attempting to unify the fundamental forces of nature. It was called the WIMP, the weakly interacting massive particle. The idea was beautiful in its simplicity. In the hot, dense first moments after the Big Bang, the universe was a seething cauldron of energy, constantly converting into particles and back again. As it expanded and cooled, most particle-antiparticle pairs annihilated each other, leaving behind the familiar matter we know. But if a certain kind of heavy particle existed, one that interacted only through gravity and the weak nuclear force, the same force behind radioactive decay, it could have survived that primordial fire in just the right abundance to account for the dark matter we see today. This wasn't a wild guess, it was a calculation. And remarkably, the numbers lined up almost perfectly. A particle with a mass somewhere between 10 and 1,000 times that of a proton, drifting through space like a cosmic ghost, barely touching anything. This became the standard model of dark matter. It was so compelling, so natural within the framework of supersymmetry, a popular extension of the standard model of particle physics, that it felt less like a hypothesis and more like a promise. And so, humanity began to build cathedrals to catch a whisper. Not temples of stone, but vaults of steel and silence, buried deep beneath mountains and under kilometers of solid rock. Places like the Sanford Underground Research Facility in South Dakota, nestled in a former gold mine, or the Gran Sasso Laboratory in Italy, tucked beneath the Apennines. These are not ordinary labs. They are fortresses against noise, cosmic rays, radioactivity, even the faint hum of human activity, all of which could drown out the faintest signal from the dark universe. Inside, scientists constructed detectors of exquisite sensitivity, tanks filled with ultra-pure liquid xenon or argon, cooled to near absolute zero, watched by arrays of photomultiplier tubes that can detect a single flash of light. The hope was that once in a great while, a WIMP from the halo of our galaxy would drift through the Earth, pass through the rock, enter the detector, and, just maybe, collide with an atomic nucleus. The recoil would be tiny, almost imperceptible, but it would leave a signature, a flash of light, a ripple of charge. That would be the moment. The first direct touch of the invisible. At the same time, other teams took a different approach. If WIMPs were created in the Big Bang, perhaps they could be recreated in the lab. At CERN, beneath the French-Swiss border, the Large Hadron Collider smashes protons together at nearly the speed of light, recreating energies not seen since the universe was a fraction of a second old. Physicists scoured the debris of these collisions, looking for missing energy that carried away by particles that didn't interact with the detectors. That missing energy could be the fingerprint of a WIMP escaping into the void. It was like trying to deduce the shape of a thief by the empty space they left behind. And still others looked to the sky. If WIMPs are their own antiparticles, as many theories suggested, they should occasionally meet and annihilate each other, producing bursts of gamma rays, neutrinos, or antimatter. Telescopes like Fermi LAT scanned the heavens, especially the dense centers of galaxies and dwarf spheroidals, places where dark matter should be thickest, searching for these telltale signals. IceCube, a neutrino observatory buried in the Antarctic ice, listened for high-energy neutrinos that might come from WIMP annihilations in the Sun, where dark matter could have accumulated over billions of years. For nearly 30 years, the WIMP paradigm reigned. It guided funding, shaped careers, inspired generations of physicists. It felt inevitable. And yet, as the detectors grew larger, the colliders more powerful, the telescopes more sensitive, the signal never came. Not definitively. There were hints, yes. Fleeting anomalies that sparked excitement and headlines. The Dama experiment in Italy claimed to see an annual modulation, a signal that rose and fell with the seasons, just as you'd expect if Earth were moving through a dark matter wind as it orbits the Sun. But no other experiment could reproduce it. Others saw single events that looked promising, only to vanish under closer scrutiny or be explained by background noise. Even the most sensitive detectors came back empty-handed, ruling out vast swaths of the possible WIMP parameter space. The WIMP miracle, as it was once called, began to feel less like a miracle and more like a mirage. The silence was deafening, not because it disproved dark matter, far from it. The gravitational evidence remained rock solid, but it forced a reckoning. What if the simplest, most elegant answer was wrong? What if dark matter wasn't a heavy, slow-moving particle that occasionally bumps into atoms? What if it was something lighter, faster, weirder? Or what if it wasn't a particle at all in the way we imagine? This wasn't failure. It was science working as it should. The absence of evidence, when you've looked everywhere you thought to look, becomes evidence of absence for that particular idea. And so, quietly at first, then with growing urgency, physicists began to widen the net. They started asking questions that had once seemed too speculative, too fringe. Could dark matter be made of something far lighter than a proton? Could it behave more like a wave than a particle? Could it interact with itself, forming structures we'd never imagined? Could there be not one kind of dark matter, but many? The hunt didn't stop. It evolved. The cathedrals are still there, still listening. But now, alongside them, new kinds of experiments are being built tuned to different frequencies, listening for different kinds of ghosts. The dream of catching a WIMP isn't dead, but it's no longer the only dream. And in that shift from certainty to open-minded exploration lies the beginning of a much stranger story. Because the longer we look into the dark and find nothing familiar, the more we must consider that what's out there might not just be invisible. It might be utterly alien to everything we know. The universe has a habit of humbling us. Just when we think we found the key, it shows us a lock we never knew existed. And dark matter, it seems, might not be a single key at all, but a whole hidden dimension of reality waiting to be discovered. The silence from the deep underground labs wasn't the only sign that something might be amiss. Even as physicists strained to hear the faintest whisper of a WIMP, astronomers were noticing something else, something in the sky that didn't quite fit the picture. The standard model of dark matter, for all its elegance, painted a universe that was smooth, predictable, and hierarchical. Small clumps of dark matter would form first, then merge into larger ones, dragging gas along to build galaxies. Simulations based on this idea, like the famous Millennium simulation, produced a cosmic web of staggering beauty, filaments, clusters, and voids that mirrored what we see in large-scale surveys. But when scientists zoomed in, down to the scale of individual galaxies and their satellites, the match began to fray at the edges. One of the earliest and most persistent puzzles is known as the missing satellites problem. According to cold dark matter, simulations where cold means the particles move slowly compared to light. The Milky Way should be surrounded by hundreds, even thousands, of small dark matter halos, each capable of hosting a dwarf galaxy. Yet when we look, we see only a few dozen. Where are the rest? Are they truly missing? Or are they there, but so dark, so devoid of stars, that our telescopes can't see them? For a while, astronomers hoped the answer lay in astrophysics. Maybe the early universe was too harsh for small galaxies to form stars, leaving their dark matter halos empty and invisible. And indeed, surveys like the Sloan Digital Sky Survey and, more recently, the Dark Energy Survey have uncovered many ultra-faint dwarfs, pushing the count higher. But even with these discoveries, the numbers still fall short. The discrepancy remains, subtle but stubborn. Then there's the too big to fail problem. Among the simulated dark matter halos orbiting a Milky Way-like galaxy, the most massive subhalos are so dense that they should easily hold onto gas and form bright, star-filled dwarf galaxies. Yet the observed brightest dwarfs, like Fornax or Sculptor, live in halos that, according to simulations, are far less massive than they should be. It's as if the universe built grand foundations, but only put up modest cottages on top. Why didn't these massive halos become luminous giants? Did something strip away their gas? Or is the dark matter itself less concentrated than predicted? But perhaps the most troubling anomaly comes from the very centers of galaxies. In the standard cold dark matter model, dark matter should pile up into a steep, dense cusp at the heart of every galaxy. Yet, observations of many dwarf and low surface brightness galaxies show something very different. Their dark matter appears to be spread out in a gentle core, like a soft pillow rather than a sharp spike. This core cusp problem has been debated for decades. Some argue that energetic bursts from supernovae or young stars could stir up the dark matter, smoothing out the cusp over time. Others point to galaxies where star formation was minimal, yet cores still exist, suggesting the explanation might lie not in visible astrophysics, but in the nature of dark matter itself. And then there are the outliers galaxies that seem to defy the rules entirely. In 2015, astronomers discovered a galaxy called NGC 1052 DF2. It looked like a normal, diffuse elliptical galaxy, except it appeared to contain almost no dark matter at all. Its stars moved so slowly that their orbits could be explained by visible mass alone. This was shocking. If dark matter is the cosmic scaffolding upon which galaxies form, how could a galaxy exist without it? Was it stripped away in a violent encounter? Or was it born that way? Then, just a few years later, another galaxy, NGC 1052 DF4, showed similar signs. And yet, nearby, other galaxies in the same group were swimming in dark matter. The contrast was jarring. It suggested that dark matter isn't always bound to galaxies in the way we assumed. It can be separated, removed, or perhaps even absent under rare conditions. Even more perplexing are galaxies like AGC 114-182, nicknamed Leoncino, one of the most metal-poor galaxies known. Its rotation curve, the very tool Vera Rubin used to prove dark matter exists, behaves in a way that's hard to reconcile with standard models. And then there's the case of the ultra-diffuse galaxy, NGC 100, so large yet so faint that its stars are spread thinner than in the Milky Way, yet it's held together by an enormous halo of dark matter. These galaxies aren't just oddities, they're stress tests for our theories. Perhaps the most dramatic challenge came not from a single galaxy, but from a pattern across many. In 2016, a team of astronomers noticed that satellite galaxies around the Milky Way, Andromeda, and even more distant systems weren't scattered randomly, as simulations predicted. Instead, they seemed to orbit in thin, coherent planes like planets around a star, but on a galactic scale. This planes of satellites problem is hard to explain if dark matter halos are roughly spherical and isotropic, as cold dark matter suggests. How do these dwarfs end up aligned so precisely? Did they form together? Were they captured as a group? Or does this hint at a deeper structure in the dark matter distribution that we don't yet understand? None of these anomalies on their own disprove dark matter. In fact, many can be partially explained by complex interactions between dark matter and ordinary matter. Stellar winds, supernova feedback, tidal stripping. But the sheer number of them and their persistence despite increasingly sophisticated simulations has led some to wonder, what if the issue isn't just astrophysics, but the fundamental assumption that dark matter is cold and collisionless? What if dark matter particles can interact with each other, not through electromagnetism or the strong force, but through some new dark force? What if they can scatter, exchange energy, even form bound states? Such self-interacting dark matter could naturally produce cores instead of cusps, because collisions would transfer energy from the center outward, smoothing the density. It might also affect how subhalers survive in galactic neighborhoods, potentially addressing the missing satellites or too-big-to-fail issues. And while it wouldn't explain galaxies entirely devoid of dark matter, it could alter how dark matter responds to gravitational encounters, making stripping more efficient. The cracks aren't in the existence of dark matter, they're in the simplicity of our model. The universe, it seems, is more inventive than our equations, and these anomalies, far from being nuisances, are clues. They're the universe nudging us, whispering that the dark sector might not be a monolith, but a landscape, diverse, dynamic, and far more intricate than a single silent particle drifting through the void. This growing tension between prediction and observation hasn't weakened the case for dark matter. If anything, it has deepened the mystery. Because now we're not just asking what dark matter is, we're asking whether it might have its own hidden complexity, its own internal life. And that possibility opens the door to ideas far stranger than anyone imagined when Fritz Zwicky first coined the term in the 30s. The hunt is no longer just for a particle, it's for a whole new physics, one that might be playing out in the shadows, right beneath our feet and all around us, unseen but shaping the fate of galaxies. If dark matter isn't the lone heavy ghost we once imagined, then what could it be? The silence of the WIMP detectors and the growing list of cosmic anomalies have pushed physicists to explore a menagerie of alternatives, each more surprising than the last, yet each grounded in real science, real math, and real possibility. This isn't wild speculation. It's a systematic expansion of the imagination, guided by data and constrained by what the universe allows. And in this zoo of candidates, the strangest ideas often turn out to be the most compelling. One of the most elegant possibilities emerged, not from cosmology, but from a puzzle in particle physics. Why does the neutron behave so symmetrically under the combined forces of charge and parity? In the 1970s, physicists Roberto Pecci and Helen Quinn proposed a solution that required a new field permeating the universe. From that field would ripple an ultralight particle, so light it would behave less like a bullet and more like a wave stretching across galaxies. This particle, later named the Axion by Frank Wilczek, after a brand of laundry detergent for its ability to clean up the problem, was originally a footnote in quantum theory. But it soon became a serious dark matter candidate. Unlike WIMPs, axions would be incredibly light, perhaps a billionth or even a trillionth the mass of an electron, and produced not thermally in the hot Big Bang, but through a kind of cosmic condensation as the universe cooled. They would flood space like a ghostly fog, oscillating at a frequency determined by their mass. And because they interact so weakly, only through gravity and a subtle coupling to electromagnetism, they would be nearly impossible to detect. Yet they could account for all the dark matter. Experiments like ADMX, the Axion Dark Matter Experiment, now hunt for them by placing powerful magnets inside ultra-cold cavities, hoping that an axion passing through will convert into a faint microwave photon. It's like listening for a single note in a silent symphony, but if they're out there, this might be how we hear them. Then there are sterile neutrinos, cousins to the familiar neutrinos that stream from the Sun and supernovae, but far more elusive. Ordinary neutrinos interact via the weak force. Sterile neutrinos would not. They'd feel only gravity, making them truly dark. If they exist with a mass in the kilo-electron-volt range, still tiny but heavier than ordinary neutrinos, they could be warm. Dark matter, moving fast enough in the early universe to smooth out small-scale structures. This might naturally explain why we see fewer dwarf galaxies than cold dark matter predicts. Intriguingly, in 2014, astronomers detected an unexplained X-ray emission line at 3.5 kilo-electron volts coming from galaxy clusters and the Andromeda Galaxy. Some suggested it could be the signature of sterile neutrinos decaying into an ordinary neutrino and a photon. The signal remains controversial. Some see it, others don't. But it shows how astrophysical observations can guide the search for particle candidates. But perhaps the most dramatic candidate doesn't require new particles at all. What if some, or even all, of dark matter is made of black holes? Not the stellar mass ones born from dying stars, but primordial black holes, forged in the extreme density of the very early universe before stars even existed. These could range from the mass of an asteroid to thousands of times the Sun. In 2016, when LIGO detected gravitational waves from merging black holes, some of the masses were surprisingly large, around 30 solar masses, raising the question, could these be primordial? If so, and if enough of them exist, they could account for dark matter. The idea was once dismissed, but it's now being taken seriously again. Microlensing surveys, watching for stars to briefly brighten as unseen objects pass in front of them, have ruled out primordial black holes in certain mass ranges, but windows remain open, especially around the mass of a small asteroid or a large planet. It's a haunting thought that the darkness holding galaxies together might be filled with ancient, invisible holes in space-time, relics from the first fraction of a second after the Big Bang. And then there's the idea that dark matter might not be a single thing, but a whole spectrum, a dark sector as rich and complex as our own visible universe. Just as the Standard Model contains quarks, electrons, photons, and gluons, bound by forces like electromagnetism and the strong force, perhaps dark matter has its own particles and its own forces, interacting only feebly with our world. In this vision, dark matter could include dark photons, force carriers that mediate interactions between dark particles. These dark photons might even have a tiny kinetic mixing with ordinary photons, allowing rare conversions between the two sectors. Experiments like the Dartlight project at Jefferson Lab are searching for exactly that. If such a dark sector exists, dark matter could form atoms, molecules, even complex structures, though likely without chemistry as we know it, since there's no equivalent of the electromagnetic force to bind electrons to nuclei in intricate ways. Still, the possibility that dark matter has internal dynamics, collisions, energy exchange, even phase transitions, could explain why some galaxies have cores instead of cusps, or why satellite planes exist. Another radical idea is fuzzy, dark matter also, called ultralight axions, or wave dark matter. Here, the particle is so light, perhaps 10 to the minus 22nd electron volts, that its quantum wavelength is on the scale of entire dwarf galaxies. At that scale, quantum effects don't vanish, they dominate. Instead of behaving like discrete particles, dark matter forms a coherent quantum wave, a Bose-Einstein condensate spanning thousands of light years. This wave, nature naturally suppresses small-scale structure, potentially solving the missing satellites problem, and creates stable solitonic cores at the centers of galaxies, exactly the kind of smooth density profiles we observe. Simulations of fuzzy dark matter produce galaxies that look remarkably like real ones, especially at the dwarf scale. It's a stunning fusion of quantum mechanics and cosmology, where the smallest scales of physics shape the largest structures in the sky. And what if dark matter is asymmetric, like ordinary matter? We live in a universe dominated by matter, not antimatter, a mystery known as baryon asymmetry. Perhaps dark matter has its own asymmetry, where dark particles outnumber dark antiparticles, ensuring its survival after the Big Bang. This could link the origin of dark matter to the origin of visible matter, suggesting a deep connection between the two sectors we've never seen. Each of these candidates comes with strengths and challenges. Axions are theoretically well motivated but hard to detect. Sterile neutrinos could explain small-scale issues but struggle with large-scale structure. Primordial black holes are simple but tightly constrained by observations. Self-interacting or fuzzy dark matter solve galactic puzzles but require fine-tuning or new physics. None is perfect. But that's the point. The fact that so many viable alternatives exist and that each explains a different piece of the puzzle suggests that dark matter might not be a single answer, but a mosaic. It could be a mixture, some axions, some primordial black holes, some self-interacting particles. Or it could be something we haven't even conceived of yet. What's remarkable is how far we've come from the assumption that dark matter must be one heavy, inert particle. The frontier is now wide open, not because we've given up, but because the evidence demands it. The universe is giving us hints through the shapes of galaxies, the silence of detectors, the glow of X-rays, and we're learning to listen in new ways. Each candidate isn't just a guess. It's a testable hypothesis, a path into the unknown. And as experiments grow more sensitive and telescopes more powerful, we may soon find which of these strange possibilities is written into the fabric of reality. Because the deeper we look, the clearer it becomes, dark matter isn't just missing mass. It's a portal, a doorway into physics beyond the standard model, into a hidden layer of existence that has been shaping the cosmos since time began. And whatever it is, it's almost certainly stranger than we imagined. What if dark matter isn't just a passive backdrop to the cosmos, but a world unto itself? Not a single substance, not even a handful of particles, but an entire hidden universe running parallel to our own, woven through the same space, yet separated by an almost perfect veil of invisibility. This idea, once relegated to the fringes of theoretical physics, has gained surprising traction in recent years. It's not science fiction. It's a serious, mathematically consistent possibility emerging from the same equations that describe our own reality. And if true, it would mean that the darkness enveloping galaxies isn't empty at all. It's teeming with structure, complexity, and perhaps even forms of organization we can barely conceive. Imagine for a moment that the dark sector isn't just a lonely particle drifting through the void. What if it has its own forces? Dark electromagnetism, dark strong force, dark weak force, governing how dark particles interact with one another. Just as protons and electrons bind via photons to form atoms, dark protons and dark electrons could bind via dark photons to form dark atoms. These dark atoms might then clump into dark molecules, dark dust, even dark stars, and dark planets. The rules would be different. No light, no chemistry as we know it, but the potential for complexity could be just as rich. And because this dark world only interacts with ours through gravity, it would remain almost entirely hidden, like a ghost city superimposed on our own, visible only by the weight of its presence. This isn't idle fantasy. The standard model of particle physics, the framework that describes all known particles and forces, has a certain symmetry and structure that doesn't forbid a duplicate sector. In fact, some theories, like those involving extra dimensions or string theory, naturally predict the existence of such mirror worlds. Even without those grand frameworks, nothing in our current understanding of physics rules out a hidden valley, a set of particles and forces that couple to ours only very weakly, perhaps through a single shared portal like the Higgs boson or a kinetically mixed dark photon. Experiments at the Large Hadron Collider have searched for signs of such portals, looking for events where energy seems to disappear into an invisible sector. So far, nothing definitive, but the possibility remains open and tantalizing. Now, take this idea further. If dark atoms can form, could they collapse under their own gravity to make dark stars? Without electromagnetic radiation to carry away heat, dark stars might shine not with light, but with dark photons, radiation we cannot see. They might live longer, burn differently, or even avoid supernovae altogether. And if dark planets formed around them, what would their surfaces be like? No sunlight, no weather as we know it, but perhaps tectonic activity driven by dark radioactive decay, or oceans of dark fluid held together by dark molecular forces. It's impossible to say, but the laws of physics as we understand them don't prohibit it. Could there be dark life? This is where even the boldest physicists tread carefully. Life, as we define it, requires complexity, stability, and the ability to store and process information. In our universe, carbon-based chemistry in liquid water provides that. In a dark sector, the ingredients would be different. But if dark forces allow for stable, complex structures, chains, networks, perhaps even self-replicating patterns, then the potential for some form of dark complexity, however alien, cannot be entirely dismissed. It wouldn't be life as we know it. It might not even be recognizable as life. But in a universe as vast and inventive as ours, why assume that complexity arises only in the visible sector? Of course, there are strong reasons to be skeptical. For one, if dark matter interacts with itself too strongly, it would lose energy and collapse into disks or clumps, contradicting observations that show dark matter halos are diffuse and spherical. So any dark forces must be weak enough to preserve the large-scale structure we see. Also, if dark atoms formed efficiently in the early universe, they might have altered the cosmic microwave background or Big Bang nucleosynthesis in ways we don't observe. These constraints mean that a rich dark sector, if it exists, must be finely balanced, complex enough to allow structure, but simple enough to remain hidden. Yet even a modest dark sector could have dramatic effects. Consider atomic dark matter, a model where two types of dark particles, oppositely charged under a dark electromagnetism, form neutral atoms. In the early universe, these atoms could scatter with each other, smoothing out density fluctuations on small scales. This could naturally produce the cores seen in dwarf galaxies, solving the cusp core problem without needing supernovae. It could also explain why some galaxies appear to lack dark matter. If a violent interaction stripped away the diffuse dark halo but left the tightly bound visible stars intact, the result would be a galaxy like NGC 1052, DF2. The same physics that builds hidden complexity could also create the anomalies we struggle to explain. And then there's the question of detection. How could we ever know if a dark world exists? Gravity is our only sure channel, but it's a blunt instrument. However, if there's even a tiny coupling between the sectors, say through a dark photon that mixes slightly with ordinary light, then rare processes could occur. A dark atom might occasionally absorb an ordinary photon and jump to an excited state, then decay by emitting another photon. Or dark matter particles could annihilate into ordinary particles through this portal, producing faint signals in gamma rays or cosmic rays. Experiments like the Alpha Magnetic Spectrometer on the International Space Station are watching for such excesses. Others, like the Lux Zeppelin detector, are sensitive enough to spot the recoil from a dark atom colliding with xenon, if the interaction is just strong enough. But perhaps the most poetic evidence would come from the sky. If dark stars exist, they might not emit light, but they would bend it. Gravitational lensing could reveal compact, massive objects with no visible counterpart. Or if dark matter accretes onto black holes, it might produce unique gravitational wave signatures during mergers. Future observatories like LISA, the Laser Interferometer Space Antenna, could detect these ripples, offering indirect clues to the nature of the dark sector. The idea of a shadow universe isn't just about particles, it's about humility. For centuries, we assumed the cosmos was made of what we could see: earth, air, fire, water, then atoms, then stars. Each time, we were wrong. The universe kept revealing deeper layers: radio waves, neutrinos, black holes, dark energy. Why should dark matter be the end of the story? Why assume that the invisible is simple? In fact, simplicity might be the illusion. The visible universe is astonishingly complex. Galaxies, stars, planets, life all arising from a tiny fraction of the cosmos's total content. It would be strangely anthropocentric to assume that the remaining 95% is bland and featureless. Perhaps the dark sector is just as rich, just as dynamic, just as full of wonder. But operating on rules we haven't yet deciphered. We may never see a dark planet. We may never hear a dark signal. But the mere possibility that all around us, interwoven with the air we breathe and the ground we walk on, there exists another reality, silent and unseen, adds a profound layer of mystery to existence. It turns the night sky from a canvas of distant lights into a veil, hiding not emptiness, but a parallel creation. And if that's true, then the search for dark matter isn't just about finding a particle, it's about discovering a new cosmos within our own. A cosmos that has been here all along, waiting in the shadows, stranger and more magnificent than we ever imagined. But what if we've been chasing a ghost that doesn't exist? What if the real mystery isn't what dark matter is, but whether it's matter at all? This is the most unsettling possibility of all, that the invisible hand-holding galaxies together isn't made of particles, hidden sectors, or primordial black holes, but is instead a sign that our understanding of gravity itself is incomplete. That Einstein, for all his genius, didn't have the final word. That Newton's laws, so perfect for apples and planets, begin to fray at the edges of galaxies and the depths of cosmic time. This idea isn't new. It's been simmering since Fritz Zwicky first invoked dark matter, whispered by a few dissenting voices while the mainstream built detectors and ran simulations. The most persistent alternative is called Modified Newtonian Dynamics, or MOND, for short, proposed in 1983 by Israeli physicist Mordechai Milgrom. His insight was startlingly simple. What if, at extremely low accelerations, the kind found in the outer reaches of galaxies? Newton's second law force equals mass times acceleration, subtly changes, not breaks down, but bends. Below a critical acceleration threshold, about 1/10 billionth of the gravity we feel on Earth, the relationship between force and acceleration shifts. The result? Stars in the outskirts of galaxies would orbit faster than Newton predicts, not because of unseen mass, but because gravity behaves differently in the weak field regime. At first glance, MUN seems almost magical. Without adding a single particle, it reproduces the flat rotation curves of spiral galaxies with uncanny precision. For decades, it outperformed dark matter models on galactic scales, fitting the data with fewer free parameters. It even predicted the observed relationship between a galaxy's visible mass and its rotation speed, the so-called baryonic Tully-Fisher relation, before it was precisely measured. To its supporters, this wasn't coincidence. It was evidence that gravity, not missing matter, was the key. But science isn't won by fitting one set of data. It's won by explaining all the data, consistently and without contradiction. And here, MOND runs into trouble. While it excels at describing individual galaxies, it struggles mightily with larger structures. Take galaxy clusters. Even with MOND's modified gravity, there's still not enough pull to hold them together. You still need some form of unseen mass, sometimes called phantom dark matter, to make the numbers work. So MUN doesn't eliminate dark matter, it just relocates the problem. Then there's the cosmic microwave background, the afterglow of the Big Bang. Its intricate pattern of hot and cold spots is a fingerprint of the universe's composition at 380,000 years old. The standard cosmological model, with cold, dark matter making up 27% of the universe, predicts these patterns with astonishing accuracy. MOND, in its original form, cannot reproduce them. It has no mechanism to explain the observed peaks in the power spectrum, which arise from acoustic oscillations in a universe filled with both ordinary matter and collisionless dark matter. Without that dark component, the physics of the early universe falls apart. Proponents didn't give up. They sought a relativistic version of MOND-1, one that could work with Einstein's theory of general relativity and handle the expanding universe. The most developed attempt is called TVS tensor, vector scalar gravity, proposed by Jacob Bekenstein in 2004. It adds extra fields to space-time that mimic the effects of modified gravity on galactic scales while attempting to match cosmological observations. But TVS's complex introduces new fine-tuned parameters and still struggles to fully replicate the success of the standard model on all scales. More recent ideas, like emergent gravity or MOG, modified gravity, offer other mathematical frameworks, but none have achieved the same predictive power and simplicity as the lambda CDM model, the standard picture of a universe with dark matter and dark energy. And then there's the bullet cluster. That cosmic train wreck remains the hardest blow to pure modified gravity theories. In that collision, the visible matter hot gas slowed down due to electromagnetic friction, while the gravitational lensing map showed the mass kept moving with the galaxies. In a dark matter model, this makes perfect sense. Dark matter doesn't interact electromagnetically, so it sails through. But in a modified gravity theory, gravity should follow the visible mass, yet it doesn't. The lensing peaks are where the galaxies are, not where the gas is. MUND advocates have proposed complex explanations involving unseen neutrinos or additional fields, but these feel increasingly like adding epicycles to save a theory, much like the old Ptolemaic model of the solar system. Still, the debate isn't over. Some physicists argue that the real issue isn't mund versus dark matter, but that both might be pointing to a deeper truth. Perhaps gravity is modified, but only in the presence of dark matter. Or perhaps dark matter and modified gravity are two sides of the same coin, a manifestation of quantum effects on space-time at large scales. Others suggest that the anomalies on galactic scales, cores, planes of satellites, missing dwarfs, might indicate that our simulations of galaxy formation are missing key physics, not that dark matter is wrong. The interplay between dark matter and baryonic feedback, supernovae, black hole jets, magnetic fields is incredibly complex, and we're only beginning to model it accurately. What's crucial to understand is that the scientific community isn't dogmatic. Most cosmologists would love to be wrong about dark matter if a better theory came along. But science demands evidence, consistency, and predictive power. Dark matter, for all its mysteries, provides a single framework that explains observations from the first second after the Big Bang to the present-day distribution of galaxies, from the bending of light in clusters to the formation of the cosmic web. No alternative has yet matched that scope. That doesn't mean we should stop questioning. In fact, the very existence of MOND and its variants is healthy for science. It forces dark matter researchers to test their models more rigorously, to confront anomalies head-on, to avoid complacency. It reminds us that gravity is the least understood of the fundamental forces at cosmic scales. And it keeps alive the possibility, however remote, that the universe might be even more revolutionary than we think. So while the weight of evidence strongly favors dark matter as a real physical substance, the door isn't completely closed on modified gravity. But if gravity is to be modified, it must do more than explain galaxy rotations. It must explain the entire cosmic story, from the quantum fluctuations of inflation to the accelerating expansion of today, without introducing more problems than it solves. For now, the invisible hand still points toward matter we cannot see. But the fact that we're even having this conversation, that we're willing to question the bedrock of modern physics, shows the strength of the scientific method. We follow the evidence wherever it leads, even into the dark. And if one day that evidence points to a new law of gravity, we'll embrace it. But until then, the hunt for dark matter continues. Not out of stubbornness, but out of fidelity to what the universe is telling us. One galaxy, one photon, one silent detector at a time. So why does any of this matter? Why spend billions of dollars, decades of careers, and countless sleepless nights chasing something we can't see, can't touch, and might never fully understand? It's easy to dismiss dark matter as an abstract puzzle for theorists, a footnote in the grand story of the cosmos. But the truth is far more profound. The search for dark matter isn't just about filling a gap in our cosmic inventory. It's about something deeper, our place in reality, our capacity to understand the universe, and the very nature of existence itself. Think about what we've already learned just by asking the question. To hunt dark matter, we've built the most sensitive detectors ever conceived. Machines that can sense a single photon, a single atomic recoil, buried under a mile of rock. We've launched telescopes that see the universe in gamma rays, X-rays, and gravitational waves. Windows into realms our eyes were never meant to witness. We've simulated the birth of the cosmos on supercomputers, tracking trillions of particles across billions of years, all to test a single idea. In doing so, we've pushed the limits of engineering, computing, and human collaboration. The technologies developed for this quest, ultra-pure materials, cryogenic systems, quantum sensors, are now finding uses in medicine, computing, and national security. But more than that, the effort has united scientists across continents, cultures, and disciplines in a shared mission that transcends borders. It's a rare example of humanity working together, not for profit or power, but for pure understanding. But the real value lies not in the tools, but in the transformation of our worldview. For most of human history, we believed the universe was made of what we could see: earth, water, air, fire, then atoms, then stars. Each time we were humbled. The earth wasn't the center. The sun was just one of billions of stars. Our galaxy was one of trillions. And now we know that everything we've ever seen, the mountains, the oceans, the stars, our own bodies, is just a tiny fraction of what's out there. The universe is mostly invisible, and that changes everything. It means that reality is far richer, far stranger, and far more mysterious than our senses suggest. It means that the cosmos is not just a stage for human drama, but a vast, layered reality in which we are latecomers, barely beginning to read the script. And what if dark matter turns out to be more than just a particle? What if it's a portal to a new physics? A theory that unifies gravity and quantum mechanics, or reveals extra dimensions, or shows that the universe is part of a multiverse. Such discoveries wouldn't just explain dark matter, they would redefine our understanding of space, time, and matter itself. They could lead to technologies we can't yet imagine, just as understanding electromagnetism led to radios and quantum mechanics led to computers. We don't know where this path leads, but history tells us that every time we've uncovered a fundamental truth about the universe, it has transformed human civilization. There's also a deeply human reason to care. The search for dark matter is, at its heart, an act of hope. It's the belief that the universe is knowable, that even its deepest secrets can be uncovered by reason, observation, and perseverance. In a world often divided by fear and uncertainty, this quest reminds us of our shared curiosity, our common wonder, and our collective potential. It's a story not of arrogance, but of humility. We look into the dark, admit we don't understand, and keep looking anyway. That's the essence of science. Not having all the answers, but having the courage to ask the questions. And perhaps the most beautiful lesson is this: the universe doesn't owe us simplicity. It doesn't have to conform to our intuitions or our equations. It can be weird. It can be complex. It can hide its truths in plain sight, wrapped in gravity and silence. And yet, we keep searching, not because we're certain of success, but because the act of seeking is what makes us human. Every time a scientist checks a detector, every time an astronomer analyzes a galaxy's rotation, every time a theorist scribbles a new equation, they're participating in one of the oldest and noblest human traditions, the desire to understand where we are and what we're made of. We may never hold a piece of dark matter in our hands, we may never see its true face, but the journey itself, the questions, the failures, the flashes of insight has already changed us. It has shown us that the cosmos is vaster and more wondrous than we ever dreamed. And it has reminded us that even in the darkest places there is light, not from stars, but from the human mind, reaching out into the unknown. So the story of dark matter isn't over. It may not even be halfway told. But whatever the ending, whether it's a new particle, a hidden sector, a revision of gravity, or something we haven't yet imagined, it will be a story of human curiosity meeting cosmic mystery. And in that meeting, we find not just answers, but meaning. Because to seek the unseen is to affirm that there is always more to discover. And as long as that's true, the universe will never stop surprising us.